Hey everybody, it's Mr. Carr again. Today we're going to be talking about 2.5 day 2. We've already talked about some of our basics with our graphing rational functions. We're going to look at a couple special cases today, and that's going to be when we graph our rational functions with what's called removable discontinuities and oblique asymptotes. Okay, it's going to be a new kind of asymptote to talk about. We're also going to spend some time solving our rational equations. So let's take a look at what does it mean by an oblique asymptote. Okay, so an oblique asymptote is going to look like this. It's instead of having end behaviors going like horizontally, it's going to be on this line like this. Okay, that line is a linear function. So what happens is if I look at a polynomial function, and this is a key part about this one, my b of x has a degree greater than 0, and a and x and bx have no common factors other than 1, then the graph has an oblique asymptote if my degree is exactly one more in my numerator. So again, what this looks like is if I have like f of x is equal to like x to the third over x squared, this will create an oblique asymptote. Okay, it's exactly 1 degree more in the numerator versus the denominator. Okay, so here's an example of that where f of x equals x squared over x plus 1. Thanks to x plus 1, we have our vertical asymptote here at -1. And then we get this oblique asymptote at x minus 1. Okay, so how do we get that equation? Well, if we can take our function, our rational function of a of x over b of x, we divide it out, we get a quotient function, this q of x here, with a remainder. That quotient is actually that linear function. So let me show you with this one right here. I can show you how to get x minus 1. If I do my synthetic division, so I'm going to do the dividing by +1. So I'll do -1, and then I got just a 1 there. Okay. So 1 squared, and I should say it's x squared plus 0x plus 0. I'm going to put 2 more zeros here. So I go through, I got 1, multiply those out, I get -1, so that's a -1 there. -1 times a -1 is a +1. So I get that, so I have a remainder here of 1. So if I divide this function out, it's going to look like this. F of x is going to be, we have x minus 1 and plus the remainder here. So f of x will be the same as taking x minus 1 plus the remainder of 1 divided by x plus 1. Okay, so really what's happening is this original f of x function is the equivalent of this after I divide it out. This section right here, that's my oblique asymptote. Okay, this is, well, so this is my remainder and everything, but the bottom line is this is what creates that oblique asymptote. So with an oblique asymptote, our end behaviors, you look at it, it's approaching that line. It's not approaching 0. It's not approaching a different number on a horizontal asymptote. It's approaching this line. So it's kind of interesting how that's going to go, because it will go on forever down, but it will, at this point, it will approach that oblique asymptote but not cross it necessarily. So let's look at an example of that on here. Determine any asymptotes and intercepts for this function. Now graph it in status domain. So I'm going to start with factoring my numerator. Okay, I want everything to be factored out. It makes it a little bit easier to work through. So x squared plus x minus 8. So that's going to give me, let's see here, x. Oh, never mind. It's not even factorable. Never mind that. We're just going to leave it like this. So x squared plus x minus 8 over x plus 3. First thing is I have a vertical asymptote at -3. So x equals -3 is going to give me my vertical asymptote. There is no horizontal asymptote. As before, we look at the degrees. This is 2 to 1. So there is no horizontal asymptote. But there is going to be an oblique asymptote because it's 1 degree more in the top. Okay, my numerator is 1 degree more than the denominator. So to find that, I'm going to go ahead and do synthetic division here. You could do long division. Doesn't have to be synthetic. Whoops. Got it mixed up for a second. So we got 1, 1, -8. So I'll go through, I got 1 times -3 is -3. Combine that to -2, multiply that out, we get +6. Combine that, we get a -2. Okay. This represents my oblique. So my oblique asymptote, oblique, is going to be y equals x minus 2. Okay. So for my behaviors, the last thing I can do is I want to find any intercepts in my x-intercepts, if I have any. That's going to come from my numerator. So when does this equals 0. The way it's set up, I just checked earlier, it's not factorable. So let's go right to our quadratic formula. So it's the opposite of 1 plus or minus the square root of 1 squared minus 4 times 1 times a negative 8 all over 2 times 1. Okay, so I'm just going to go ahead and plug this all in my calculator at once just so I can get my two answers real fast. Give me 1 second on that one. Okay, so from my calculator, I'm going to get two irrational values here. I'm going to get x is equal to negative 3.3, let's go 37. And my second value is going to be 2.37. Okay, also I can look for my y-intercept. If I look at that one, that is going to be f of 0. So that's going to be 0 squared plus 0 minus 8 over 0 plus 3. So that's going to give me a negative 8/3. So my x-intercepts, I've got points at negative 3.37, 0, 2.37, 0, and 0, negative 8/3. So let me plot those points along with my vertical asymptote at negative 3. Okay, and I'll get to plotting the horizontal or the oblique asymptote in just a minute here. So negative 3.37, so I'll estimate about right there. 2.37 be about right there. And I'm crossing at 0, negative 8/3. So it's almost a negative 3 right about here. Okay, so the other thing I want to do again is graph that oblique asymptote, y equals x minus 2. So that's going to be right here, minus 2, and then it's going to be a positive 1 for its slope. So oblique looks like this. Okay, so based on how my graphs look, could probably, let's say we're going to do something where I cannot cross. You know what? I'm going to go to let's go to Desmos real quick because I'm having a little bit of trouble picturing this myself. Whoops, Desmos. Okay. All right, there it is. Yeah, that's what I thought I was going to do. So I'm going to go ahead and graph y equals x minus 2 here. You can see that's the oblique asymptote for my end behaviors, and it splits off. This is towards the vertical asymptote. Same thing here is going towards the vertical asymptote. And I'm crossing at these 2 points here and here, as well as this value here. So I thought that's what it was. So I'll do something like this. Here. Whoops. This again, the curve is going to go towards the asymptote, so it's going to get closer and closer to that while it goes that way. All right, so that's my oblique asymptote. The next scenario to talk about is what happens when we have a removable discontinuity and what creates that. So determine any vertical and horizontal asymptotes. So I'm going to first start off by factoring my numerator and denominator so I can see some of these pieces. X squared is going to be a +3 and a -3. In my denominator, I'm going to have -3 and +2. This right away, I'm going to talk about what creates the whole. Normally, if I go to my vertical asymptotes, I would have two of them. I can see this and this. But when I go to the graph of this, that one off, we only have one there. So what happened to the other one? So the first one that's occurring is happening at x equals -2. We see that one. But why is it not happening at 3? Seems like it's going through right there, no problems. But if I get really close here, it's going to be up right there, undefined. We have a hole in the graph. So we get that hole by this. Notice how we have x minus 3 and x minus 3 as common factors. So because of that, I'm actually going to cancel those out and reduce this down a little bit. So h of x, I don't want to necessarily rewrite that completely, but in a way, it's like if I graph x plus 3 over x plus 2. Okay, so I'm going to cancel that out for now. Now, my vertical asymptote, as we saw, is definitely at a -2 here. So x equals a -2. My 0, I do have a y-intercept, or let me do my x and y-intercept, I should say. My x-intercept is going to happen when just x plus 3 equals 0. So that's going to happen at -3, 0. So again, that's what happened here. -3, 0. Okay. So I got my x-intercept. Let's do my y-intercept. Okay, my y-intercept is going to be at 0. And if I plug that in, so let's see here, h of 0 is going to be 0 squared minus 9 over 0 squared minus 0 minus 6. So it's just going to be the negative 9 over negative 6, which is positive 3 over 2. So my y-intercept is at 0, 3 over 2. And I totally forgot to do horizontal asymptote because I do have that here since my degree is the same. So it's the ratio of my leading coefficients. So that's going to be y equals 1 over 1 or just 1. Okay, now I'm going to go ahead and plot my vertical asymptote at -2, horizontal asymptote at 1. My x-intercept is at -3, 0. It's crossing here. My y-intercept is at 0, 1.5. So the biggest thing here is how do I represent that hole in the graph? So one way of finding that now is I'm going to use this kind of simplified version. Remember, the hole happens at +3. Okay, so according to the vertical asymptote, it can't be 3. According to the 0, it can cross at 3. So I'm going to evaluate h of 3 as long as I use this version. 3 plus 3, 3 plus 2. So that's going to give me 6 over 5. So what that means is my hole exists at this point. The hole is going to be at +3, 6 over 5. Okay, so if I go here, +3, 6 over 5 is like 1.2. So it's right here. Okay, again, that's where it happens here at this hole. You can't quite see it, but if I approach from both directions, it's going to approach 1.2. Okay, so even I can just put that in as a point. 3, 1.2. Sorry, just want to little trouble here. Come here. There we go. Okay, so that's what's happening on that curve right there. Okay, so again, it is approaching the horizontal asymptotes in both directions there. So for my graphing, I can do this now. Just continue on approaching that horizontal asymptote and over here as well. Okay, so again, that's with our oblique asymptote and our hole or removable discontinuity. So the last thing we'll talk about for today is our solving of our rational equations. I got 2 examples of that. So one option is, if it's something like this, I can add this rational expression over to the other side. Like this one can come over here. So I could say that, let me write it this way. I want to turn it into like x over 1 is equal to 4 over x minus 6. So I'm adding that whole expression over. Now we can cross multiply. If I have it as a proportion, we can do our cross multiplication. So x times x minus 6 is equal to 1 times 4. So x squared minus 6x equals 4. It's a quadratic, so if I want to solve that, I'm going to bring the -4 to this side, make that equal to 0. Now, what I need to do is, because I cannot factor this, I'm going to go ahead and do my quadratic formula in this case. So I'll do negative of -6 plus or minus the square root of -6 squared minus 4 times 1 times -4 all over 2 times 1. Okay, so I'll go to my calculator at this point. Yes. And we get x is equal to -0.606 and positive 6.606. Now, as it was also irrational value, so I technically could have done this. I could have done x equals √13, whoops, √13 plus 3. And well, technically I would have done backwards on that one. 3 plus the square root of 13, or it would have been 3 minus the square root of 13. Okay, those are my 2 answers as well. So that's our first scenario here. I always like to do a quick check for solving rational equations. One thing that x cannot be is a positive 6, which I'm fine here. These are two non-6 answers. But that's a quick check to make sure for any extraneous solutions. Because like when I go on to the next one, I might get extraneous solutions. Here, I'm going to offer a slightly different method here. Whatever your common denominator is, so multiply the equation by a common denominator. Okay. When I do that, it's going to get rid of all my denominators, so it's no longer a fraction in like this fraction form. So in this case, if I multiply everything by x minus 1, I'm going to take x times x minus 1. But then when I multiply the second part, this is going to go away. So it cancels out with x minus 1. So I have plus x now. This also cancels out, so I get 3x minus 2. Now it's just a matter of solving it out. So I got to distribute here. So I got x squared minus 1x plus x equals 3x minus 2. Okay, we can combine these. Those are going to cancel each other out. But because it's a quadratic, let's make it equal to 0. So x squared minus 3x, and then plus 2 to the other side is 0. This one's factorable, so let's go ahead and do that. X minus 2 times x minus 1 is equal to 0. So I solve those out. I get a positive 2 and a positive 1. So that's my final answer. I'm done, right? Except for one thing. This positive 1 will not go back into the original equation. Okay, if I try to plug it in, it would not work. So this original equation, it's kind of helpful to actually look as my first step. What can x not equal to? And that's a positive 1. So because I solved it out and I got to x equals 1, that's extraneous. Okay, so that one's extraneous. So my only answer here is actually x equals 2. Okay, all right, and that's it for today. So again, we talked about graphing with obliques, graphing with holes, and solving our rational equations. All right, take care, everyone.